guys. Today we're going to be looking at Chapter 5, Lecture 12, and we're going to be looking at Learning Objectives 1 and 2. Within Learning Objectives 1 and 2, we're looking at potential kinetic energy, and we're looking at our system and surroundings. So let's just go ahead and get started looking at energy, which is what this chapter is all about. And this is the ability to do work or transfer heat. Okay, and then within here we have our work, which is the push and pull of an object. So the energy used to move an object or cause an object to move. And then our heat is energy used to cause the temperature of an object to increase. We call this evaluation of energy thermodynamics. So when we're studying energy or energy transformations, that's our thermodynamics. Okay. And then specifically, we have thermochemistry. So looking at those energy transformations, but of a chemical reaction. Or I guess I should say the study of. Let's go with that. So here our chemical reactions are what are causing these energy transformations. Okay. So energy itself, we can look at it in terms of work and heat, or we can look at it in terms of kinetic and potential. So energy can be either kinetic or potential in nature. So it can either be movement energy or it can be energy that's stored. So our potential energy is stored energy. So this is going to be the energy that an object has due to its position or chemical composition. So if we have something at the top of a hill that's about to be pushed over, that would have a lot of potential energy. Or food has a lot of potential energy. As we digest it, it can heat up our body, and that is going from a potential energy to a kinetic energy. So we've got energy of position, boulder at top of cliff. And then due to composition, something like food, or octane, something like octane. Octane by itself doesn't do anything, but it's got a lot of stored energy, and when we burn that, it produces a lot of energy, so that'd be potential energy. Okay, now, one of the most important types of potential energy that we look at in this class is electrostatic potential energy. And this is the energy due to two charged objects being in close proximity. Okay, so here we're talking about two charges some distance away. And we have a equation that relates the two, where we have our energy, EL, it's just electrostatic, is equal to funky looking long fat K times by Q1 times by Q2, all divided by D. There are Q1 and Q2 are the charges on particles. D is distance, and then K is a proportionality constant. That's going to relate our units, joules for our energy, coulombs for our charges, and we're going to have meters for our distance. So it's going to be 8.99 coulombs squared. Okay, so what this basically says is that we have two charges, the magnitude of the charge and the distance between the charges are going to affect how much potential energy we have between the two charges. So greater magnitude, smaller distance, greater electrostatic potential energy. So this is generally why we think of things that have large charges that are small. Those are going to be more attracted to other large charges that are small. Okay, let's now look at our kinetic energy, which is our energy of motion. A lot of the times when we think about our chemical reactions, we're thinking about in terms of kinetic energy because we're losing and gaining heat, and that heat is the molecular motion. So and heat is caused by molecular motion. So we could usually think about kinetic energy um, when we're thinking about those reactions themselves. Okay, so something will have kinetic energy if it has motion, right? So we have a falling as a great example of something that has kinetic energy. Okay, and then other things are going to be molecules. Anything in the world has, as long as we're not at absolute zero, we have kinetic energy. So 0 Kelvin, we call that absolute zero. And this is when we no longer have molecular motion. So everything besides things at absolute zero are going to have kinetic energy due to that molecular motion. Okay, so everything has kinetic energy. Fantastic. We using the following equation. Squared. So the more massive, the greater the velocity, the greater the kinetic energy. Okay. We can look at what are called energy units. So what units we are going to be solving for when we're thinking about our equation. We will not solve for this. We will not solve for our electrostatic potential energy. You just have to understand how that equation works. We will, however, use our kinetic energy to solve for, or we'll solve for our kinetic energy using mass and velocity. So most of our energy units is going to be in joules. That's because this is the SI unit for energy. And remember that 1 joule is equal to 1 kilogram times by meter squared divided by second squared. And then another unit that is very common is the calorie, which is going to be abbreviated as just CAL. And we have 1 calorie is equal to 4.184 joules. This is an exact number. So infinite sig figs. Then we also have a large C calorie, which is equal to 1,000 small calories. So 1 big C calorie is equal to 1,000 small C calories, or 1 kilocalorie. Okay. Now that we know the units, let's look a little bit more at energy. We're looking at energy transformations, or the transfer of energy, looking at both our system and surroundings. So our system and our surroundings are what we're going to be looking at during energy transformations, where our system is going to be the thing we're observing or studying. And this could be a reaction. So the molecules involved in a reaction. So looking at that reaction, we can see the energy that it absorbs or emits. So this is what we want to know the energy of. This is not generally a simple process. It's usually actually very complex. So we can't generally look at our system. We will actually have to almost always look at our surroundings. Okay, now we have something, a special case, where we have an isolated system. And isolated system is where we're trying to basically have no contact from the system with the surroundings. So this is a thermodynamic system that can't exchange energy or matter outside of the boundaries of the system. This is not something that we really can accomplish. Attempt at this is like a thermos. So a thermos is an attempt to do that. Okay, now our surroundings. Surroundings are going to be everything else besides the system. Almost always we're going to be thinking about the surroundings in terms of things that can actually transfer heat and matter with the system. So it's going to be in contact with the system. Okay. So, as in close enough. For energy transfer. Okay. We can think about a system and surroundings, like doing a reaction in a piston. That was not very good. Let's try that again. Okay. So we've got our piston right here, and then in here we have a reaction. Okay. And the reaction itself would be our system. And then our surroundings would be the cylinder, the piston, everything beyond. So as the reaction takes place, it will transfer energy with this whole system right here, or this whole surrounding right here. And in the case of this, it'll probably push up on to the piston, or it could push down, the surroundings could push down on the system as well. Okay, and that is all for today, or for this lecture. We're done. We're going to move on to the next learning objective in the next video. Bye. See you guys later.